Now, in this example, we are going to express the concentration of species J has a function of conversion x. In this case, for a liquid phase reaction. Soap consists of the sodium and potassium salts of various fatty acids such as stearic, palmitic, lauric, and myristic acids. The saponification for the formation of soap from aqueous caustic soda and glyceryl stearate is reaction 3A plus B gives 3C plus D. So if we take A as the limiting reactant, so we divide all this reaction by 3, we will have capital A plus 1/3 of capital B will give us C plus 1/3 of capital D. Because this is a liquid phase reaction, the density is considered to be constant, therefore the volume B is equal to B0. So we recall that the concentration of A is going to be the number of moles Na divided by the volume, and as the volume is equal to the initial volume, we will have that Ca is going to be Na divided by B0, but Na, we must remember that is Na0 times 1 minus x. So we will have that Ca will be Na0 times 1 minus x, all that divided by B0, and this is equal to Ca0 times 1 minus x. Theta B is equal to Cb0 divided by Ca0. Theta C is equal to Cc0 divided by Ca0. And theta D is equal to Cd0 divided by Ca0. So here we have the stoichiometric table for this liquid phase swap reaction. In the second column, we have the symbol A, B, C, D, and I, the inert. Initially, of A, we will have Na0. Of B, we will have Nb0. Of C, we will have Nc0. And of D, Nd0. And a total, and the inert is the initial is equal to the inert at the end. So the change for A is minus Na0x, that is the amount of A that is going to be consumed. For B, 1/3 of Na0x, because the relation in the reaction of these two substances. For C, we will have Na0x because it's forming and it's positive. For D is 1/3 of Na0x. So the remaining, for A, we will have Na0 times 1 minus x. For B, we will have Na0 times theta B minus x divided by 3. For C, we will have Na0 times theta C plus x, and for D, Na0 times theta D plus x divided by 3. In concentration, for A, we will have Ca0 times 1 minus x. For B, we will have Ca0 times theta B minus x divided by 3, and so similar expression for the rest. Okay, now we are going to use the equation that we just obtained in this example 2, but we are going to use it in this example 3, in which they ask us what what is the limiting reactant? And then they say, using the table of example 3.2, calculate the concentration of D when the conversion of A is A 20% and B 90%. If the initial mixture consists only of A at a concentration of T moles per cubic decimeter, or which is equal to 10 moles per liter, and that will be of 2 moles per liter. Solution: only the reactants A and B are initially present, so theta C, theta D will be 0 because they are 0. So for 20% conversion, we will have that the concentration of D is going to be CH0 times X divided by 3. So this is equal to CH0 is 10 times X, in this case 0.2, the 20%, divided by 3. This is equal to 0.67 moles per liter, or equal to 0.67 moles per cubic decimeter. So that's the concentration of D. And the concentration of B will be CH0 times theta B minus X divided by 3. So this is going to be CH0, which is 10, times theta B, and we will get it from the concentrations of B0 and C0 at the entrance. So that is going to be the concentration of B0, that is 2, divided by CH0, that is 10, minus X divided by 3, in this case 0.2 divided by 3. That will give us a total of 1.33 moles per liter. Now, for 90% conversion of A, the concentration of D again will be CH0 times X divided by 3, but in this case X is going to be 90%, 0.9, so it's going to be 10 times 0.9 divided by 3. This is equal to 3 moles per liter. And for B, the concentration of B will be CH0 times theta B minus X divided by 3. So again, this is going to be 10 for CH0 times 2 divided by 10, which is theta B, minus 0.9 divided by 3. That will give us minus 1 mole per liter. So, negative concentration. What went wrong? Well, what happened is that 90% conversion of A, it is not possible because B is the limiting reactant. So, example 4. Manipulation of the equation for the concentration of J as a function of conversion. Show under what conditions and manipulation the expression for the concentration of V for a gas flow system reduced to the given for a variable volume batch reactor. Well, here the solution is that for a flow system, the concentration is defined as the concentration of B is equal to the molar flow rate of B divided by the volumetric flow rate B. So the molar flow rate and conversion are related by FB equal FA0 times theta B minus B divided by A times X. And combining these two equations, we will have that the concentration of B is equal to FA0 times theta B minus B divided by A times X, all that divided by the volumetric flow rate, B. And if we recall that the volumetric flow rate at any time at any time t will be B equal B0 times 1 minus plus epsilon x times P0 divided by P times T divided by T0. This equation for the volumetric flow rate B is only for a gas phase reaction. If we substitute the volumetric flow rate, that will give you that Cv, the concentration of B, is the volumetric flow rate of B divided the molar flow rate of B, divided volumetric flow rate. So this is going to be FA0 times theta B minus B divided by A times X, all that divided by the expression for the volumetric flow rate, that is, in this case is going to be B0 times 1 minus plus epsilon X times P0 divided by P times T divided by T0. So recalling that FA0 divided by B0 is equal to CA0, we will obtain that CV is equal to CA0 times theta B minus B divided by A times X divided by 1 plus epsilon X times P divided by T0 times T0 divided by T. These expressions get simpler when we take into account that a lot of reactions are at pressure and temperature constant.